Okay, welcome back everybody. This week we are going to be talking about function notation. So we're still kind of on the track of talking about graphs and different ways to represent them and different ways to describe them. So remember from before, some really important terms we've been talking about, the first one being domain. So when I'm talking about domain, I'm talking about the x values on the graph. Now sometimes we also call those independent. Right? Independent because we don't actually control how those change. They change consistently. And our y values, so the range, is the y values or the dependent. So depending on how our x values change, our y values are going to look a little bit different. We also looked at two different kinds of graphs, right? So here we've kind of got two different types. This first one here being individual points that are not connected. Remember, this is important because our domain and range is going to look different depending on how our graph looks, right? Because we're trying to show us what the possible values are. So for a graph where we only have dots, we call that a discrete graph. And in a discrete graph, we have dots that are not connected. So when we're talking about possible values, we're talking about a set of possible values that are not connected. Our other type, our continuous graphs, are ones where those points are connected using a line. So when we're talking about domain and range, we're going to have all of those values in the middle be possible. So here for this first one, we have a discrete graph. So when I'm talking about the domain of a discrete graph, remember I'm talking about the x values. So as I go along, I'm doing that check to see what is possible. So I see here, this is my first point. Remember, I'm working from left to right. So -3, I have a point. -1, I have a point. At 0, I have a point. At 1, 2, and 3, I have points. Now notice that when I'm doing my domain and range here, these are not connected points. They are unique points, and so I have to list them. Same with for my range. Now for range, let's just switch my color. I'm going for the y values. Oops. Right, so as I'm moving along, once again, from smallest to biggest, so starting at the bottom this time, looking for values that are possible. So here I've got my first one at -2, -1. Now, even though I have two dots here, just by writing that once, I show you that it's possible, and so I don't need to write it twice. I see a point at 0, and same thing with that positive one. I've got those 2 points, but just by writing it once, I show you that's possible, and that's all that we need to do here. Now, the second thing that's asked me is whether or not it is a function. So remember that a function is a special relationship where every x value, so every independent value, has a unique y value. So if I put 2 in for x, there's only going to be 1 point that falls on x is 2. So one of the things I can do here is what's called that vertical line test, right? So where if I do vertical lines, so a line at every x value, there will only be 1 point. So for this graph, that's true, right? There's only 1 point on each line, and so this is a function. So for this graph, we've got a line, so that's going to be continuous. And so for a continuous graph, I have to show all of those values. So once again, I'm going to look from left to right, and I'm looking for, I'm going to do blue because I'm doing domain. So this is my smallest value. And then if we look along here, as I move, every single value is possible. right? Because I have a line that goes through every value until I hit the high end, oh my god, of my range. So for continuous graphs, we have kind of like that sandwich, right? So for my domain here, I go from -3 to +3. And because these are open circles, I'm not going to put a line under because they're not part of my data set. And my range, similar, I'm going to start at the bottom and I'm looking for the first point that hits. And then as I move up, I'm seeing that as I move up, there's always a possibility, right? Until I hit this point. That's my highest point. So for my range, I'm going to be going from -3 all the way up to +4. Now down here, open dot, no line underneath. But up here, when a line goes through, that's a possible value, so I have to put a line underneath it. Now we're going to do that vertical line test to see whether or not this is a function. So once again, we're looking, when I draw those vertical lines, how many points are hitting. So once again, all along here we only have 1 point, so this is a function. So this is another continuous graph. And so we're going to start on the left and move over, and I see this is my furthest point. And as I move across, all of those points are possible until I get to the other side. So for my domain, I'm going to go from +1 all the way over to +5. And because they are going through as solid lines, those are equal. For my range, starting at the bottom, and as I move up, these are all possible until I get to the top. So for my range, I went from 0 all the way up to 4. And once again, solid lines are part of my graph. Now I'm going to do a vertical line test here and see. So I've got one line there. Now notice when I draw this vertical line in, we actually have 2 points where my line goes through. That means that this is not actually a function, because when I plug in the value x of 2, there's 2 possible answers. Doesn't mean that there's not a relationship there. It just means that it doesn't fit into this specific type of relationship. So it's not actually a function. Another continuous graph. And so on the left end, and then as I continue, these are all possible values all the way up into the end here. Now this time when I look at the end point on my graph, it doesn't actually end in a point. It ends in an arrow. Now remember that what that arrow means is that that is going to continue forever. And so if it's continuing in the negative direction, that's going to continue to negative infinity. And I actually have the same thing on the other end, so that one's going to continue to positive infinity. And here I don't put the lines under because technically we can't never be equal to infinity. And so we're going to do our range as well, so my lowest point and my highest point. And once again, those are ending in arrows, so once again, we're going to go to infinity. Now, is this a function? Well, we're going to have to do that vertical line test to see how many points are being hit. And if you have like a ruler or a straight object, you can just move it along and look. You don't actually have to draw all these lines in. So because there's only 1 point on each line, this is a function. So what we're going to look at today that's a little bit different is a special way of writing these functions. So when we have a function, a graph where every x has only one y, we use what's called function notation. And it's just a special way of writing this. So they're very similar. So remember before we had that y equals 4x minus 1. Well, if we have a function, instead of writing y, we write what we call f of x. And what this shows is that we have a function of x. So we have a graph where our y values, where there's only one y value associated with every x value. The rest of the equation is the same. So the only thing that's changing here is that instead of writing y, the dependent variable, we're writing this function. So this right here is that function notation. So we read it, the way that we say it is f of x equals. So when we're talking about this, we've changed this now. So our f of x is the same as our y value, where our x is the x value. And so that's important here because this f of x is not two variables, it's one. It's written together, and it kind of means something together. And so when we're looking at these graphs, we can actually sub numbers in, right? We talked about that before. If we wanted to find a y value, we can sub it in. So here, what does f at 3 mean? Remember that f at x, right? F at x was y. So when I have f at 3, it's the function value when x is negative 3. And that function value is the y, right? So it's the y value when x is negative 3. So over here it says find f at negative 3 for f of x is 5x squared minus 6x plus 1. So this negative 3 is the x value. So a little bit weird here because f at x is y, x is x, obviously. So that f at x is a special value. So what I can say here is for f at negative 3, now this negative 3 is equal to x. So anywhere in the equation where I see an x, I'm going to replace it with negative 3. And when I sub something in, I sub it in brackets. So this negative 3 is going to sub in here in brackets. And that's squared, so it's still squared. Minus 6, I've got another x, that becomes negative 3 plus 1. Once we've subbed that in there, it's just our basic BEDMAS to find the answer. This f at negative 3, remember that that's not actually something I'm going to solve. That means y, right? It means the variable y. We're trying to find that value. So my first step, remember I'm following BEDMAS, right? So my first step here is going to be brackets. Do I have any? No, because when I say brackets, I mean operations inside of a bracket. Here I don't have any operations. I just have brackets to hold my negatives. So it means my second step is my exponents, which I do have. I have this squared. So negative 3 squared is going to be positive 9. Next step, division multiplication. So I've got two multiplications to do here. 5 times 9, 45. Negative 6 times negative 3, positive 18. And then my last step here is going to be that addition and subtraction. So we're going to go 45 plus 18 gives me 63, plus 1 gives me 64. So f at negative 3 is 64. So if I was looking at that as a point in my graph, remember I said that this negative 3 was my x value, right? So remember if we had a point, my point is going to be x and y. So here my x is negative 3. And when x equaled negative 3, the function, the y value, was 64. Okay? So this f at 3 is not something I'm trying to solve. It's a value in itself. It's the function when x is negative 3. And so here, this says, what is f at 2 for this function, for this equation? So f at 2 is equal to, and remember, that means that x is 2. So anywhere in my equation where I see x, I'm going to substitute positive 2 in. And once it's subbed in, I'm just plugging in my BEDMAS. So do I see any brackets? No. Exponents? No. Division, multiplication? Yes. I've got a 3 times 2 here. And then just the addition and subtraction. So 6 plus 1 is 7. So what this means is when x is 2, y is 7. F at negative 2 for this other function. So when f is negative 2, that means that in this equation, and you will have different equations. You can use the same numbers of different equations. We're just looking to see what the y values are. So negative 2, I'm now going to sub that into my equation. And then once it's subbed in, we're just doing that BEDMAS. Do I have any brackets? No. Exponents? No. Division, multiplication? Yes, I have one here. So we're going to go 7 minus 3 times negative 2 is going to give me, so there's 2 ways I can do this. I can go 3 times negative 2, or I can go negative 3 times positive, or negative 2. It's going to give me the same answer. So 3 times negative 2 give me negative 6. And then addition, subtraction, 7 minus negative 6. Remember, negative is the same as a positive. So that's like saying 7 plus 6 is going to give me 13. So that means when x is negative 2, y is 13. So remember here, this f at negative 2 is the same as saying y. It's the y value when x equals negative 2. So remember, a graph is just another way of representing an equation, just like an equation would be. So here, this is f at negative 2, or at positive 2. Remember that 2 is my x value. So I'm looking for the point where x is 2. What would the y value be? So on my graph, I find that x is positive 2. And I look. If I go up, there's the point. So for this graph, when x is positive 2, my y is positive 1. When f is 6, so f at 6, this is your x value. So when x is 6, y is 4, right? That would be the point 6 and 4. At 3, we have 2. So that would be the point 3 and 2. And we can actually do this the other way as well. So if I said, what would f at x be for positive 3? Now remember, this is the y value here, right? We don't know the x value here. We know the y value, right? This is the y value on this side. So I'm looking for the point when y is 3. So for this one, I'm just going to swap colors so we can actually see this. We're going to actually go to y is 3 to figure out, oh, well, that's at positive 1. So f at 1 is 3. Okay? So why do we bother? Why do we even say f at x when we can just say y? And really, it's just to specify, just like with domain and range. Like, what's the point in writing domain and range? Because it tells us something about the graph, right? And so with these function notations, it tells us, oops, I don't know why I read this. It tells us that the graph we are looking at is a function. Meaning that every x value will have only one y value, right? And so that can be really important to know when we're looking at graphs, because if you get something that doesn't match that rule, it might signal that you're doing something wrong. So let's try that here. So remember, once again, the number in the bracket here is actually our x value. So we're going to go to x at positive 3. 1, 2, 3. Where is the line hitting for y? It's hitting us right at 0. So f at 3 is 0, which remember would be that point 3 and 0. F at negative 2. So negative 2. Now notice in this graph, it looks like there are 2 dots here, and that might be confusing. But this one is open. Now remember when we were doing those intervals, we didn't put a line under for an open dot because technically that open dot is not a value. It might be a starting point or an ending point, but it's not actually part of our graph. So here, this is not actually part of the graph. So the y value that we're looking at is down here. It's going to hit at that positive 1. F at 0. So when x is 0, my line, and it doesn't have to be a point, right? A line going through is the same as having a point there. It's hitting at positive 3. F at 6. 1, 2, 3, 4, 5, 6. Where's that line, right? Because it's where our line's going through. Positive 4. And I'm just going to give you another example of doing that backwards, right? So if instead you had like f at x is, let's try this one. I'm trying to find a point here. Let's do this one. 0. So here, that's the y value 0. Now, the tricky thing with our y values is that you can have multiple x values. So we could have f at 1, 2, 3, 4, 5. Negative 5 is 0. F at negative 3 is 0. And f at positive 3 is 0. That is okay for a function. You can have the same you can have the same y values. They just have to have different x values associated with them. All right, so this is what you're going to be doing today. You're going to be going through and mostly calculating with function notation. So have fun.